All right. How you guys doing? Is this working fine for you? Okay. No? Some yes, some no? Is it just not scanning, or what's going on? Yeah, the Wi-Fi is bad. It took my computer a minute to get going as well. All right. I'll leave this up here for a couple moments longer. And if you have any issues, let me know. I did take a look. It seems like you can mark yourself as present, late, excused, or absent. Or I can mark you in that way. So what I'll say is, why don't we do this? If you need to miss class and you email me and I excuse your absence, medical or whatever, feel free to log in and mark yourself as excused during this day, because you'll have this day to do it, and that'll help me out a little bit. Feel free to mark yourself as late if you email me and say, hey, I'm catching this online, I had to do whatever, but I'm still watching today. Again, it's still up to you to be an adult and sign in and actually watch the lecture. And I'll be happy because you can just give me that feedback and I'll give you credit for that, and that'll help me track, okay, how many people are actually participating, showing up, using this. How is that going for you during the semester? And again, today and Thursday, I'm not actually going to track these in terms of your grade. Starting a week from today, I'll track these as part of that participation score. Okay, so if you can do that, that'll be great. Like always, just communicate with me if you are, if you do have to miss for some reason. Okay, with that, again, you'll have, if this didn't work for you, you'll have all day today to log back in and grab that. Okay. All right, so today I'd like to, oops, let me back up a couple slides here. Start here. Today I'd like to talk to you about reactions and reactors, and maybe start on. So one thing I want to make clear is a distinction between, and actually let me see if I can turn this light off. There we go. One thing I'd like to make clear, wastewater, right? And you've got flow going through it, coming in continuously and leaving continuously. These are two very different reactors, obviously the size, but also one has a flow rate and the other is just sitting here, okay? So as we'll discuss today, we can label the different types of reactors, and you can also imagine there's two examples already, and the third one would be if you kind of have something like a pipe where water can be flowing through it, but it's a long object where the stuff at the beginning is not mixing with the stuff at the end. That ends up very relevant for how we understand the processes that are going on inside. Okay, so that's the deal. Today we're going to talk about reactions and then reactors, where we might do the reactions. And possibly we'll get to chemistry, that's more so on Thursday. Okay, so a reactor. That's the container. So I have here a little picture of this box. We can draw input lines and outflow lines. We often will have something that's well mixed. We have a little mixer. And as we'll describe, we would call this a continuously stirred tank reactor, or some people call it, so that's a CSTR. You might hear it called a CMFR, continuously mixed flow reactor. We have different labels for it, but the deal is a typical one would be we're mixing it and we're flowing water in, and water is also leaving, okay? Could apply for an air phase thing, but again, we're doing water. All right, so a few general terms I'd like to make sure are very clear before we really launch into too much more. And if you stop and think about it, a MGD for million gallons per day. That's, a lot of times we'll try to stick with metric units, but you'll see this very often. You'll hear, if you're ever working in the wastewater or water treatment industry, oh, it's a 5 MGD plant. That's a kind of a medium. and a lot of times we will have C, and at some time T, or just left as C as the current. Some water that enters will immediately be leaving a few of the molecules. If it's perfectly mixed, that means as soon as it touches it, all of those new molecules that entered are now dispersed completely, randomly, then some of them will be immediately leaving. That's our completely mixed setup. We'll talk more about it and why that's relevant. But in that case, the hydraulic retention time will be some average of how quickly that one left and the slower ones that keep getting mixed around and not leaving until they finally leave. What's the average time for water to stay in there? And we have a formula for that, that is theta is equal to V over Q. And this is one particular equation I'd like you to memorize. I'm not going to put it on the formula sheets because it is very, very intuitive when you stop and think about it, and it's very, very important. You should simply know this for the class. Okay? So this one, theta equals the volume divided by the flow rate. Commit this one to memory. And if you forget it, remember that this is a detention time. Time in units of time, right? So to get to time, given something about the reactor, if you take, let's say, bless you, cubic meters divided by cubic meters, I don't know, per day, you will find that the volumes cancel and the time comes to the top. So if you think about it as volume per time, you can get time out of that. So if you ever get confused, look at the units, just think to yourself, with volume and flow rate, how do I get time as my units? You'll derive your equation for hydraulic retention time. All right? So make sure to have mastered that. It's a simple concept, important, and we'll use it a lot. All right. Next up, we will talk about rates. Now, rates and rate constants are a bit different. So if let's take an example, say that some entity is losing $10 million from its account per day. You might think to yourself, wow, that's a very large amount of money per time, right? Now, what would the rate constant be? How would we describe that? It actually could be very small. It could be a very small percentage if the net balance in there is huge. So if we're talking about, I don't know, the US Treasury or something, that's going to be a very big number it's changing from. And so as a whole, that might be a small percentage. And that percentage per time would be the rate constant, whereas the amount per time would be the rate. So a rate is an amount per time. This is our, if we take a look at our units, we'll describe this as the change in concentration per time typically. We could also describe this in mass per time. So if we take this concentration per time across some volume, we get mass per time. Okay, so the rate will be effectively a mass per time ablation rate as a mass per time. And we relate that to the input rates, the output rates, and whatever reactions might be happening in our system. Okay, so a concentration per time multiplied by a volume gives us this mass per time rate. Then a rate constant, what we need from a rate constant in terms of units, or to understand it, is, and we'll call rate constant K, italicized lowercase k. And so as we'll see, that per time as a unit is actually pretty common. So if you take 5% of your bank account and increase it by that much every year, that's a 5% interest rate, but I would say that's a rate constant. That 5% is a rate constant, and if you had $10 in that account, your rate of gain is what, 50 cents per year? That's pretty small, but if you had a very large number, and maybe I got that wrong, if you had a very large number, that actual rate can be a very much larger number. You could be earning $10,000 per year, even with the same rate constant. Okay, so you're getting a little window here, and we'll describe this in detail with, okay, what kind of a rate order is that, and how does all that work in a couple minutes. But I just want to give you the pieces, the kind of the definitions here. So we've got volumes, obvious, flow rates, makes sense, concentrations, that's what we're dealing with in terms of how much stuff is there per volume, hydraulic retention time, and then rates and rate constants. So rate constants feed into the rate to give us, and you'll see the rate constant number here. And these are the core pieces of the mass balances we'll be dealing with. Okay, I'll add anything else if we come to it in different problems, but almost all of the class is going to be this kind of stuff. There will be a couple things like sedimentation where we're not necessarily doing mass balance as much. Most of the principles apply, and then we'll use some mass balance techniques to improve sedimentation. So as we move on into the treatment technologies, this will be a very common theme, okay? So make sure you're comfortable with what all this means. Okay, so let's talk a little more about this hydraulic retention time. This is a key design parameter because it encompasses both the size of your reactor and how fast you can move water through it. So if you have space constraints, that might mean you must flow water faster. So your treatment, whatever you're doing, has to be more aggressive or act faster. On the flip side, if you have plenty of space, maybe you can slow it down and use less chemicals or use less of whatever to do the job. So the amount of time we're able to give the water to flow through our system matters a lot. And again, that's V over Q for the residence time. Now, I want to give you a quick little visual example of what we call a tracer test here. And this essentially is going to show you how we might consider a liquid flowing through a reactor. And for our class, we're generally going to take it for granted that we're going to have ideal reactors where we don't worry too much about inconsistencies of mixing. But here you'll see there are places where, if we add this dye as a tracer, it's called a tracer test, it's moving along through. Some places don't get a lot of the concentration. Some places get a lot of it, perhaps too much of it, right? So in reality, when we make a reactor, we do have to worry about these things, and even some certain zones that just don't get a lot of, let's say, the treatment. Let me speed this up a little bit. So we'll see a little spot develop here that is just not getting much of this dye, and it's what we might call a dead zone. So there are things that we could do mathematically to account for all of this, and one of these pieces would be called a tracer test. Just kind of wanted to give you a visualization of the types of things we might imagine we could deal with in a real reactor. Fortunately, what we can do for the moment is simply assume our reactors are going to be ideal reactors, okay? So if we wanted to deal with non-ideal reactors, we use things like tracer tests to see how long the water stays in there on average. So this key design parameter, hydraulic retention time, might change if it's a non-ideal reactor, okay? And in that case, we have to modify this equation a little bit because not all of the volume is being used, or however we want to think about it. But for our case, we're going to keep things ideal. And kind of the other point of that is you saw that the amount of water flowing through it, that speed at which it was going through, we could see how long that blue plume stayed in there. And we could time that and say, okay, here's the residence time. If I knew the volume, then I could know the flow rate. Or if I knew the flow rate, I could know the volume. Okay? So that's the structure itself. All right, so order, first order, and second order. And the reason we call them this will be very apparent in a moment. We don't typically use second order reactions for our class because we're going to keep it a little simpler. And that's great news for you because that means you don't have to remember too much calculus. Okay? There's a few derivations that if we were doing second order, it gets a little bit more difficult and occasionally impossible to do explicitly. But for zero and first order, you will be able to do all of this and derive them. And I'll just remind you a couple tiny pieces of calculus today, and you'll be like, oh yeah, I remember that. And you'll be fine. Okay, so zero order. Here's our rate equation. I mentioned it last time. We're going to say the rate at which some concentration changes, which again we often put in some volume, will be dc dt. Okay, that's our rate. We're going to say that's going to be equal to, could be a growth equation, positive, or a decay reaction, a negative. Rate constant, there's that order. Okay, that means if we have a zero order reaction, c to the power of 0 becomes what? Exactly. Thank you for paying attention here. Okay, exactly. So if c goes to 1, then it doesn't matter how much c is there. For a zero order reaction, doesn't matter how much you already have. This would be equivalent to saying, I don't care how much you have in your bank account, give me 10 bucks a day. Or I'll give you 100 bucks a week, something. If it doesn't matter how much is in your bank account, c to the 0. Okay, c being how much is in your bank account. All right? We can imagine my bank has a 1 liter volume. Okay, and then if I have $100 per liter, we're putting it in concentration units. So if it doesn't matter what concentration of money I have in my bank account, then what order is this? This is a zero order. Okay? So a zero order reaction. So if we take the first one here as 0, and we'll take this next one as a first order, and the last one as a second order, we can graphically describe this. Let's take a growth reaction. Could look something like this. Maybe I start with some amount at time 0, and I'm growing, and it doesn't matter how much is in there, it's growing at the same rate over time. All right? And we could even make a little slope and say, hey, that slope is how the concentration changes per time. And if we look at what happens if we put c to the 0 power, our dc dt equals simply k, right? Plus or minus k. So in this case, k is equal to dc over dt. This is just as simple as back to physics and you have a velocity. Okay, well, now we're just describing how the amount of something in a volume of water is changing. Likewise, we could describe the speed of something moving, the distance traveled. We could describe money in a bank account. Okay, zero order doesn't care how much is there already. Of course, we could have a negative. I'll change colors and do negative for that in a moment. All right, for a first order, now we have c to the 1 power. So now we have dc dt is equal to plus or minus k times c. So this is where we get the bank account analogy back and say, now we have some interest rate, and it does matter how much you have in there. Okay? If you have a small amount, the calculated rate, the amount that will change, is a smaller amount because c is smaller. So if you think of the left side here as this is the amount that changes given some time, equating that to here, if you have a small c, your amount is small, even if your k is large. Okay? And if you have a very small k and a large c, again, not a big change, at least not within reference to how much c you have. But both will matter, and it will matter to the first order. Okay, c to the 1 power is how we could describe that. For the second order, it's going to be the same deal. dc dt is equal to k times c squared. Of course, this could be positive or negative. So in the case of a positive, If we just simply have dc dt equals k times c to the 1 power, we're going to start at 0 because when... actually, I guess maybe we could add some constant if we wanted to, but let's start at 0 for this. And say if we're starting at 0 and then we add some, then we'll have some exponential growth, right? Something like that. And in the case of a second order equation, it's going to be pretty similar.